All right, so my name's Steve, and I worked on a team that consists of John and Thomas Erickson, who's not here today. And the three of us, we designed fairly similar robots. We started off with some open source designs for plexiglass that was to be laser cut. And then from there, we took that kind of open source design and modified it greatly to meet our needs. And so I ended up remodeling all this stuff in DesignSpark, which is a 3D tool like the CAD software that you used. It's from a company called DesignSpark out of the UK. It's also an open source. We spent a lot of time on our actual hardware design, and this design consists of a Pololu X2, Orangutan X2 control board, and 4 infrared sensors, 1 point in each direction. And then in the front we have 2 ultrasonic ping sensors that were going at an angle with a little bit of overlap. And then we also had an IMU on the back. This is a Pololu, actually it's just a compass and magnometer, and an accelerometer. So one of the challenges that we had with this particular design, in the Pololu X2 Orangutan, I was having a lot of trouble getting the library support set up to use, because I decided to go with C++ versus just straight C, because I'm from an object-oriented programming background. I'm just a little bit more comfortable doing that. But I spent a lot of time doing that. Our team also spent quite a bit of time kind of changing the design here and there. But in the end, we did get a good platform built. And I've also got this servo here on the front with a 3D printing claw to grab the cans. So one of the biggest lessons I learned on this project, this was my first robot, by the way. I've never built robots before. So it's been a whole lot of great learnings and a lot of fun. But one of the things that I really learned on this is that we spent way too much time designing the hardware, and we didn't spend enough time working on the software. So as we got closer and closer to the competition, the pressure got higher and higher to kind of figure things out. And we'd already gone down this route of designing a fairly complicated software to run it, and pull all these sensors and do a lot of different calculations. So in the end, I really only got some basic behaviors working. And so by the date of the competition, I had it had the ability to basically drive in a straight line and detect when it had run into something. I'll talk a little bit about that in a second. And then reverse direction. And that's pretty much all I got it to do. So I just named it Havoc because I figured it was going to run around and bump into things and go the other way and maybe throw off some odometry to my competitors. So at that time, I just called it Havoc, and we had some fun watching it kind of run into things. One of the things that I did figure out how to do was design, I guess what we're calling now a virtual bumper. And using some of the features of the controller and the motors, but the controller specifically has got the ability to do current sensing on each motor. And so in my code, I've actually written it to read the current sense every single time it goes through its loop and save those readings off. And I would average the last 50 readings to understand what my average current is doing. And because I knew it was going to be on a flat surface, for not going over hills or into bumps or anything like that, I just said, well, I'm going to take a look at the average, what it takes to run the current, to run around in straight lines and stuff, and then add another amp and a half or so to that and call that my threshold. So that when I run into something, if I just drive along and I'm running into something, the amperage starts ramping up on the motors, and I can immediately tell that I'm running into something. And so then I change directions and do some sort of correction to get around it. And that actually turned out to work quite well. In practice, when I'm driving around, it'll bump into stuff, and that 50 samples goes by in a flash under a second. So it just looks like it immediately knows, backs up, turns, and goes. It works out pretty well. The other thing that I learned was on the infrared sensors. In order to also get really clean, or better readings anyways on it. In addition to not pulling it so quickly, you should probably look at putting a little 10 UF capacitor in line, and that helps filter out some of that noise on the power.
That was between VCC and ground, right, Steve?
Yeah, through VCC and ground. And it's called out kind of in the data sheet, but a lot of people just kind of overlook that as well.
Where is the noise coming from? The motors?
The noise coming from these infrared sensors. The IR sensors are real noisy. Yeah.
So the sensors inflict noise on their own beacons.
Yeah.
Pulse, they have a super high current LED that they're pulsing.
It's a 200 milliamp pulse.
Yeah. And so by putting that capacitor on there, it filters that out so that that noise doesn't go back into the controls and everything else.
You'll get a lot of noise just from PWM drive of the motor.
Yeah.
Because that's it could be a several amp pulse that you're hitting it with. So.
Yeah. And the other thing I did was I just got one battery that runs this whole thing, but I did put in line a Pololu buck regulator to power a secondary board and most of my actual sensors. So the noise from the motors and the noise from other things could be on a separate power line. So it's going through a secondary level filtering with that regulator. So, and that's it. So next year I hope to have a lot more of the programming done and be a lot more competitive. So we had a great time.
We're going to do another Roborama.
Yeah, I'll mention it later.
Okay.
Yeah, I'm going to let everybody do their thing and finish, Steve.
Yep.